teach Petrography courses in English with the lecture notes of the Middle East Technical University, Department of Geological Engineering. Remember, the Mining Association is a worldwide channel. That's why we have to be broadcasters in English. We hope to have publications in other world languages in the future. Remember, learning should no longer be individual, but global. Hand in hand with the whole world, sometimes we may have amateurish mistakes due to our technical inadequacy. I remind you that we are preparing these publications out of impossibility.
Principles of Mineralogy and Petrography. Principles of Mineralogy and Petrography. Assist. Professor Dr. Fatma Toksoy Cogsall 1. Offer. The goals of this course are to teach students to. The goals of this course are to teach students to have an appreciation of the relationships among the structure of a mineral, its chemical composition, and its physical properties. Be able to identify samples of the common minerals and common rock types. Begin to understand factors that affect the stability and occurrence of minerals and assemblages of minerals rocks. Composition of the EAN of the Earth or inner planets, including the Earth accreted from the solar nebula about 4.6109 years ago after accretion compressed and became very hot due to gravity. Quote, Big Bang Theory. Quote, Big Bang Theory. Differentiated NTO a series of layers. Due to differences in density. Crust, mantle, core, earth layered structure, heterogeneous composition, high density material, Fe metal alloys, core. Mantle dense Fe Mg silicates, crust lighter aluminosilicates, Mg Fe. Na, K aluminosilicates, oceanic and continental metamorphic discontinuity. Solid inner core, Fe rich with minor S, K, and P, Lehman discontinuity to liquid core, approximately same as inner core Gutenberg discontinuity. Crust. Extreme chemical differentiation. During formation and evolution of Earth. Most off-side elements like Fe, Ni, Company, Pin Earth's core. Lithophile elements. C, Al, B, L, C, Na, K, Rb, Ca, Mn, U. Strongly fractionated out of the mantle and into the Earth's crust. Considerable compositional differences B2 the oceanic and continental crust. Diagram showing the oceanic crust at the island of Hawaii and at the Great Valley of California. Oceanic crust, continental crust. Earth's crust. Earth's crust, various rocks, igneous, plutonic, volcanic and hypabyssal from melts at high T, in liquid state sedimentary at surface conditions of low P and T from aqueous solutions, metamorphic at depth at higher P and T due to changes in solid state. A general classification of rocks. Earth's crust. 95% igneous rock, or its metamorphic equivalent, e.g. basalt, granite, igneous, schist. 0.8 most abundant elements in crust equals 99 Wt% and approximately volume composition. O, C, Al, Fe, Ca, Na, K, Mg. Most common crustal mineral silicates, e.g. quartz, CO2, aluminosilicates, e.g. K feldspar, orthoclase, calci 308, oxides, e.g., hematite Fe2O3 total earth composition 99% Fe, O, C, Mg, Ni, S, Ca, Al. Difference due to core and mantle. Rocks deal with petrography minerals building blocks of the rocks deal with mineralogy. Part 1, MI, Mineralogy. Introduction. Mineral subject of mineralogy mineralatin word logos greater than 2,500 minerals 200 known most common and abundant. From the earth crust. Greek word knowledge. Mineralogy. Mature science. Science of mineralogy, study of the physics and chemistry of natural, solid, crystalline materials. Why study minerals? Why study minerals? Minerals fundamental to environmental sciences, earth sciences, geochem, geophysics, way atoms arranged in rocks. Atomic environments in rock homogeneous from the scale to the scale, 7 orders of magnitude rocks aggregates of minerals. Atomic environments in rock. Mineralogy, solid state geochemistry. Definition of mineral. Mineral, naturally occurring. Homogeneous solid. Definite, not fixed chemical composition. Anodid atomic arrangement. Formed by inorganic processes. Mineral, a natural, crystalline phase. A chemical compound must occur naturally somewhere and be stabilina to study in the lab. Minerals naturally occurring distinguishes man-made substances, g. Synthetic, e.g., synthetic. Diamond, many compounds made in the lab that are not minerals unless not found in nature. Minerals. Minerals homogeneous solid, chemically homogeneous down to the atomic scale, means consists of a single, solid substance and it be divided into simpler chemical compounds, excludes gases and liquid. H2OA mineral buters water nota mineral as ice in a glacier liquid higbutan some or deposits mineraloid. Minerals definite, but not fixed, composition specific but variable chemical formula Mg, CO3, 2Mg if and only if Fe, Mingineralika, Mg 0.7 Fe 0.2 Mn 0.1, CO3, 2 dolomite poline definite chemical composition CO2, an H2O mineraloid. For a given mineral, substitutions of similar elements possible. Original crystallinity destroyed by radiation from radioactive elements present in the original structure. Mineral anodid atomic arrangement, chemical formulas determined by the atomic structure as an internal structural framework of atoms, or ions, arranged in a regular geometric pattern equals crystalline solid repeated patterns in 3D position of an atom in the structure. Definite predictable crystals, periodic arrays of atoms, solid slack and ordered atomic arrangement. Amorphous egg. Volcanic glass, limonite and metamite minerals, e. Zirenbio. Glauconana. Minerals and organic processes, at least one occurrence formed by inorganic processes, inorganic in origin but some biogenically produced inorganic compounds, means. Not mineral, however organic compounds, petroleum and coal, macerals. E.g. calcid be organisms to form shells, also in igneous and metamorphous environments, but g. aragonitine shell and pearlopal, mount, fluorite, some phosphates, sulfates and Mn oxides, pi and elemental S of bacterial origin. Minerals: gold, silver, diamond, graphite, pyrite, marcasite, sphalerite, zolpolite, fluorite, calcite, apatite, olivine, garnet, zircon, pyroxene, amphibole, mica, quartz, feldspar, zeolite. Natural solids, not minerals, granite, basalt, limestone, rocks, wood, coal, organic, non-crystalline, opal, obsidian, pumice, glass, non-crystalline. Mineralogy requires an understanding of chemistry, elements, electronic structure, bonding, chemical analyses, forms of extals, interrelationships between humans and the natural environment, mineral genesis, environments of formation, e.g., ocean floor versus subduction zone, determinative mineralogy, physical and chemical testing, analytical equipment, classification schemes. Physics, physical properties, density, electrical properties, cleavage, hardness, magnetic properties, etc. Crystallography, the structure of minerals, internal and external, geometry and trigonometry, symmetry. General classification of classification of minerals. Rock-forming minerals. Rocks consist of various minerals. Useful for industry, e.g., feldspar, right pointing arrow, ceramics, glass, industrial minerals. Ore minerals, high concentrations of metallic elements, e.g., chalcopyrite, CEU, cinnabar, Hg. Metals and valuable elements, extract gemstones for decorative purposes, e.g., diamond, ruby, emerald. Gemstones. Secondary minerals, rock-forming minerals are decomposed and altered, HP rocks brought to surface, Lieutenant, LP, by tectonic forces, G. Clay minerals, serpentine minerals, etc. Naming of minerals. Physical property. Magnetic, right pointing arrow, magnetite, Fe3O4. Predominant element, right pointing arrow, chromite, Fe2O4, bar, right pointing arrow, barite, baso4, locality, Franklin, New Jersey, right pointing arrow, franklinite, ZnFe2O4, bandama, right pointing arrow, pandamite, Ca4b10019, 7H2O. Coloralbus, L. White, right pointing arrow, albite, null, C308, rodent, G. Rose, right pointing arrow, rhodonite, MnCO3. Scientist. Benjamin Silliman, right pointing arrow, sillimanite, Al2CO5. Crystallization. Crystallization, crystals from solutions, melts and vapors. Desiderate states, random distribution, change in T, P, conc. Atoms. Join in an ordered arrangement, crystalline state. Crystallization from solutions. Evaporation of water from Naxoln. Soln. More Na plus and Cl per unit volume remaining water. Not hold all the salt in the Soln, precipitation of solid salt. Slow evaporation. Few centers of crystallization. Big crystals, rapid evaporation. Many centers of crystallization. Small crystals. Port increase. Dissolve more salt into solvent by forcing solvent into crystal street. Increase in thermal vibrations. Breaking ionic bonds. Port decrease. Saturated Soln. Supersaturation. Crystallization. Crystallization from melt. Much the same process as from a sol. Rock melt magma. Uncombined ions with considerable amount of cross-linking of ions or ionic groups CO4. Ions free to move in any direction in molten state. Cooling magma. Two opposing tendencies. 1. Thermal vibrations tending to destroy nuclei of potential minerals. 2. Attractive forces tending to aggregate ions into X-street. Decrease of T and P in a wet melt, decrease of T and increase of P in a dry melt. Eliminates destructive effect of 1, increase attractive effect of 2. Crystallization from vapor phase. Solid crystals without the intervening liquid phase from vapor seg. Sublimates of S formed near volcanic vents. Crystal growth. Crystal growth crystal growth first stage enucleation. Random formation of large number of potential nucleonstable high surface energy equals surface area, volume small nuclei high surface area many atoms on the outer surface with unsatisfied bonds and saturated most nuclei redissolve. So, if a nucleus survive, grow rapidly enough to increase its volumeto, reduce its surface energy, internal atoms have completely satisfied bonds, reach a critical size. The nucleus survives, grows at a relatively diminished rate. In ionically bonded crystal down pointing arrow during crystal growth order decretion of ions where surface energy greatest, unsatisfied bond, corner, max, edge, intermediate, surface, minimum. In non-ionically bonded crystal down pointing arrow atoms accrete on outer surface as clumps of atoms down pointing arrow steps along which new outer layer of crystal. Chemical bonds and classification of minerals. Chemical bonds and classification of MiCal bonds. Forces binding atoms, ions or ionic groups. Electrical in nature. Forces binds. Responsible for most mineral properties 5 principal types. Covalentionic metallic hydrogen van der Waals strength. Covalent. Electron sharing atoms. Inert gas configuration. Elements near the middle of the periodic table. C, Al, S. 2, 3, and 4 vacancies in outer electron orbitals. Up to 4 covalent bonds with neighboring atoms. Minerals with covalent bonds. Insoluble. Great stability, very high melting points. Two Platums equals 1s 22s 22p 63s 23p5 overlap an outer orbital. Perhaps can share whereby 2e, fill, the remaining 3p shell of each Cl in a strong bond right pointing arrow Cl2 shared E bond C4 valence electrons each C atom fill the bonding orbitals B electron sharing with 4 other C atoms forming very stable firmly bonded configuration tetrahedron shape with a central C atom bonded to 4 others at apices very rigid structure diamond CCC bond angle fixed at 109.028. Ionic. Ionishonic. Atoms. Strong tendency to achieve inert gas configuration with completely filled valence shell of an atom transferred to that of another one. Na 1s 22s 22p 63s 1 right pointing arrow Na plus 1s 22s 22p6 plus ECL 1s 22s 22p 63s 23p5 right pointing arrow CL 1s 22s 22p 63s 23p6. Electron lost by Na. Picked by attraction by the way Na plus and Cl. Ionic or electrostatic bond. Moderate hardness and specific gravity. Fairly high melting point. Easily disrupted by polarized solvents water. Poor electrical and heat conductors. Bond length. Interionic distance. Shorter bond length, stronger bond. Reverse relation by the way melting point bond strength. Reverse relation by the way melting point reverse relation by the way hardness. Linear relation by the way bond strength and charge number. Metallic. Electrons freely move through the crystal structure. No affinity to any particular nucleus. Without disrupting the bonding mechanism. Very weakly tied valence electrons into metal structure. In metal X's. Positively charged metal ions with their filled electron orbital surrounded with a Lie-charged dense cloud of valence electrons. Occurs in native metal minerals such as O, Ag, Cu. High conductivity, ductility. Generally low hardness. Hydrogen. Form structure by attraction by the way oppositely charged ends of molecular spallar molecules. Electrostatic bond by the way plus Lie-charged H plus and Lie-charged ions O2, N3 plus. Shape of H2O molecule. Polarween crystallized. Ice mineral each O atom is bonded to 4 neighboring O atoms in a tetrahedral arrangement by intervening hydrogen bonds. Common in hydroxide mineral group O groupnet behaves strictly as spherical anionic group. Asymmetric and polar. Dipole effect. In many of layered silicates with hydroxyl group micas and clays. Air walls. Usually electrically neutral molecules. Cl2, N2, O2. Molecular solids. Occupied valence orbitals be electrons used in covalent bonding. Polarization of an atom or a molecule. Dipole effect. Residual charge on the surfaces. Neutral atoms or molecules into a cohesive structure. Van der Waals or residual bond. Graphite and crystalline sulfur. In graphite. Covalently bonded. Van der Waals. Covalent bond. Well-developed cleavage low hardness. In sulfur. S8 rings. C6 rings. Covalently bonded adjacent rings. Van der Waals. Low hardness, low melting point. Crystals with more than one bond type. Crystals with more than one bond type. Minerals. With only one type of bonding. Rare. Most. 2 or more bond types most. Graphite. Strong covalent bonding. Weak van der Waals bonding. High melting point perfect cleavage. Layered silicates. Sheets of strongly bonded silica tetrahedral layers relatively weak ionic and or hydrogen bonds plus perfect basal cleavage. Chemical classification of minerals. O. Most abundant element chemically minerals. Considered as oxides principally. C. Second most abundant element Great affinity by the way O and C. Strong covalent bonding. Silica tetrahedron CO4 4 dash CO4 4 balanced by various cations. As in Mg2CO4 mineral group silicates. Minerals. Other cations. Join with O. Oxides. EGMT, Fe3O4. Oxyanions. Example. Carbonates. CO3-2. Calcite CaCO3. Nitrates. NO3-2. NiToKNO3. Sulfates. SO4-2. Gypsum CaSO4, 2H2O. Chromates. Cro4-2. Crocoidpubcro4. MOLYBDATES. Mu4-2. Wolfenite PB Mu4. TUNGSTATES. WO4-2. Scheelite CaO4. Borates. B3O4-O3-2. Colemanite Cab3O4-O3. H2O. Phosphates. PO4-3. Apatite Ca5PO4-3F-ClO. ARSENATES. ASO4-3. Erythrite Company 3 ASO4-8H2O. VANADATES. VO4-3. Vanadinite PB5VO4-3Cl. URANYLATES. UO2+2. Carnotite K2UO2-2VO4-2. 3H2O. O. Oxyanion minerals with close packing of O2 with small interstitial cations. Depending on type of interstitial cations. OXYANION minerals. O. Strong ionic bond with H+ hydroxide minerals. Hydroxyl anion, O. E.g. Brucitem G, O2, goethite FeO, O. S. Next important anion. Combination with metallic cations. Sulfides, G. Galena PbS, sphaleretanes, chalcopyrite cuffs 2. Halogens of clan F. Halides. E.g. halite nickel, fluorite Caf2. Native elements. Not form any chemical compounds. As elements. Noble elements with metallic bonds. EGO, Ag, PT native metals. Semimetals with bond type by the way covalent and metallic native semimetals, G. As, by. Non-metals with mixed types of bonding. Native nonmetals, G, C, S.